Wind, the invisible force moving everything around us, just like that. But as early as 5000 BC, sailboats were propelled along the Nile River using wind energy. Nowadays, we understand wind and we can use it to produce energy. In 200 BC, simple wind-powered water pumps were used in China, and in the 11th century, windmills were used for grinding grain in Persia and Middle East to produce food. And in 1887, the first known wind turbine for electricity production was built in Scotland. More and more wind turbines are still being built to avoid the omnipresent lurking danger of global warming.
What is the correlation between the global warming and the ice cream in my hand? But look, it's melting. So this is our challenge. Can we design and build a 3D printable wind turbine to solve this energy crisis? This is our team.
So we had 5 design constraints while we built our turbines. The first one is the turbine should fit in a box of dimensions 400 millimeters by 100 millimeters by 150 millimeters, and this was due to the size of our 3D printer. The second constraint is the turbine should rotate clockwise. Our third constraint was the maximum power coefficient should be reached at a TSR between 3 and 8. The fourth design constraint is the maximum angular velocity shall not exceed 3000 RPM. And the last constraint, which we found most challenging, was to keep the total mass of our wind turbine below 200 grams.
We decided on our design direction very early on. We elected a 2-bladed design with maximum radius. This would ensure good aerodynamic efficiency and maximum power. We elected to use the SG60 airfoil family, designed specifically for small wind turbines. Going for maximum blade radius meant designing a turbine that could be printed folded on itself. Weight would be our main limiting factor.
Our main goal was to extract the maximum possible power from the wind. As the wind flows over the blade, some of its kinetic energy is converted to rotational energy by the action of aerodynamic forces. A local blade section experiences 2 velocities as the blade rotates, an axial velocity due to the wind flow and a tangential velocity due to the rotation. The actual velocity that the blade sees is the vector sum of the two, defined as the relative velocity. As shown in the diagram, the angle of incidence alpha is the difference between phi and the twist angle theta. In an attempt to maximize the power output, the torque and hence the tangential force component on the blade need to be as large as possible. This is achieved by maximizing the glide ratio CL/CD. After comparing the performance on different airfoils, we chose to go with the SG6043 airfoil as it leads to the highest CL/CD values for our range of operation. The optimum angle of attack was deduced after interpolation as the one that gave the largest ratio. In order to keep alpha at an optimum constant value, theta must change accordingly as phi changes. Therefore, as the radius of the blade decreases towards the root, then theta must increase. What is more, an increase in relative velocity as r increases means that the chord length must decrease to keep the load and deflections within acceptable limits. The twist angles and chord lengths were calculated with Schmidt's formula for a design TSR of 4.5 and optimum alpha around 6 degrees by dividing the blade into 8 sections. Schmidt's was preferred over Pett's formula as it accounts for the rotation of the wake and therefore for the conservation of angular momentum. The aerodynamic loads were calculated by implementing the blade element momentum theory into a MATLAB script. This included an iterative procedure that computed the axial and tangential induction factors at each blade section. After the values converged, they were used to calculate the tangential and axial force coefficients. The coefficients were then used to calculate the aerodynamic loading and torque on the blade. Prandtl steep loss factor and the Glued criterion were applied for increased accuracy.
So some might say structural analysis is the most important part of this project, and I'll leave the decision up to you. So my team tasked me with making sure our turbine blade can withstand aerodynamical and centrifugal forces while being a mere 200 grams. So I'll take you through the process now.
The most distinctive part of our turbine blade were its thick cylindrical roots. We forgo any aerodynamical advantage we could get from this part of the turbine blade, and this served a purely structural purpose. As we can see from our 2 graphs, stresses and bending momentum are highest along the root tip, and that's why we chose the cylindrical shape. Using simple beam theory, we calculated our blade deflection along the length of our blade. Our thick cylindrical root increased the stiffness of our blade and deflection was minimized. And the maximum deflection occurred at the tips where it came to be 4 millimeters. Every structure under the influence of aerodynamic forces is faced with strong instabilities that cannot be prevented even by increasing the reliability of the design. This destruction has been created due to a specific force, and this value of force is created because of a specific relative velocity of flow that is called the flutter phenomenon, and the fluid speed destruction is called flutter speed. Recognizing the flutter speed, we can endure the safety of structure under aerodynamic forces. In structures such as turbines, flutter velocity is a velocity which must not be reached by a turbine under any circumstances, and in not considering the flutter phenomenon in our initial design became our downfall.
Once the main design parameters were set, we could model the wind turbine in the popular and easy-to-use CAD software PTC Creo. The blades were first constructed by blending airfoil sections which were scaled and rotated through their quarter cord. We were inspired by the structure of owl feathers which enable super silent flight and added trailing edge serrations. We hoped this would help with noise or performance. Recognizing the blade tips would generate most of the power, we decided to have a cylindrical root and give up any aerodynamical advantage. It would be a purely structural member. The nose cone was to be as small as possible. It would need to house the hub and a hinge to fold the turbine. The chevrons on the surface increased the glue surface area. With the model ready and technical drawings submitted, the next step was manufacturing.
You, the audience, may ask yourselves, how are these gorgeous wind turbines are produced? Right, the manufacturing process consisted of two major parts, hub production and 3D printing of the turbine. As seen in this video, the hub was made from a simple cylinder of aluminium that was turned, drilled, cut and engraved. We expected the turbine to be slightly heavier than the maximum allowable weight of 200 grams. We predicted around 3 to 5 grams of excesses according to the density of ABS and the volume of the turbine. We would easily send these excesses off and meet the weight restrictions, however, the final weight turned out to be 225 grams. This amount of residues could not be polished off without changing the structural stiffness or aerodynamic performance, hence we decided to stay with this weight. During the polishing stage we slightly damaged the serrations of the trailing edge, but this had a little impact on our power outputs.
We're here at the proving ground of our design. So we wanted to see the power output of the wind turbine at different wind speeds. So we sped up the wind tunnel velocity to 6, 8, 10 and 12 meters per second.
First, the wind tunnel velocity was sped up to the desired one and an electric brake was applied which created torque. Using the brake, the turbine rotation was slowed down more and more to create a higher and higher power output until a maximum was reached when the relative wind would approximately come from the angle of attack associated with the maximum lift coefficient of the airfoil. The power oscillation, which occurred at all wind speeds at an angular velocity of about 1,600 rpm at high RPM of over 2,700, were due to resonance. The natural frequency of the structure was reached, which caused the blades to oscillate back and forth. Thus, the wind came from different angles of attack, and therefore, the power output oscillated. Unfortunately, our wind turbine fractured before reaching a wind speed of 12 meters per second, so we couldn't receive any data for that.
After letting our emotions cool down following the failure, it was time to go over the results and draw conclusions. Excessive vibrations caused one blade to fail catastrophically at the root. These images show how the nose cone wall sections gave out. Upon inspection, it's easy to see the design was too weak. Despite the failure, our turbine tests were very encouraging. It obtained an average max CP of 0.3 at an average TSR of 6.0. Blockage effects in the wind tunnel affected these results. It is difficult to evaluate the influence of our features on performance, as we had no control test. No way of knowing if it indeed controlled trailing edge flow or reduced noise. It certainly looked nice. Definitely reduced bending deflections. It may be worthwhile to revisit this design, looking to optimize structural and aerodynamic efficiency of these sections, just as industrial wind turbines do. The hinge worked very well, and the chevrons fit smoothly. The walls around the hub were definitely too thin. To improve on this design, it would be interesting to redraw the nose cone, adjust the root section shape, and drill holes into the metallic hub to reduce weight. Vibration analysis could also help determine the onset of resonance and reduce amplitude. Overall, we're very proud of our design, but recognize the very few faults it presented.
How are these wind turbine blades are produced? Wow, how lucky we are to stand here in front of the farm tree which actually produces the wind turbines. Look, This one has only one blade. It's not yet time to harvest it.